Hello everyone, I'm Tachan Yang. Today I'm excited to present my project, Marine Oil Spill Identification, integrating multispectral features with a two-stage deep learning framework, supervised by Professor Chai Lin. First, let's look at our background. Why is detecting marine oil spills so critical today? We can categorize the importance into four main pillars: ecological preservation, economic security, public health protection, and regulatory enforcement. One of the key data sources we use is satellite optical imagery. Its main advantage is high interpretability, making it easy for human experts to recognize oil spills. Furthermore, we extract rich spectral features from the sensor data, providing multi-layered information that allows our model to distinguish oil. However, applying deep learning to optical imagery will face several unique challenges. The most critical is spectral similarity, where oil spills can look very similar to waves and lakes. Additionally, environmental sensitivity, such as lighting or cloud cover, presents further issues that affect the final detection performance. We utilize the model's datasets and the MarineX model as our experiment materials and the baseline. Our expectation is to achieve a 50% improvement in oil IOU performance. Model's datasets consist of 174 scenes, where each scene contains multiple images. Furthermore, it covers 50 different categories, including oil spills. Here we can see the RGB imagery alongside their ground truth labels across various scenarios. Next is our proposed methodology overview. We add more spectral features and utilize a two-stage deep learning framework based on the baseline model. This is our workflow diagram, which we will introduce in 3 parts. In data preprocessing, we calculate 7 extra spectral indices from the original 11 channels and simplify the 50 categories into 2 classes, oil and others. We add 2 types of indices. First, cross discrimination, which include the FAI, FDI, and SI help distinguish oil from similar things like algae and shadows. The second type is background calibration, such as MDWI, NDVI, NDMI, and BSI, helps the model ignoring the coastline and spatialize the marine background. In training, we use a free-fall cross-validation strategy. The goal of Stage 1 classification model is to filter out images without oil. The key metric is recall because we don't want to lose any real oil pixels. The Stage 2 segmentation model identifies oil at the pixel level. The key metric is oil IOU to ensure high segmentation quality. In hybrid evaluation, the Stage 1 model acts as a filter to remove images without oil. The remaining images go to Stage 2 for pixel level identification. We then combine the results to get a final IOU performance. Looking at the results, by using EfficientNet B2 and ConfNext as Stage 1 model, the oil IOU increased to 0.818 and 0.867 respectively. Our best configuration achieved an improvement of over 20% compared to the original paper's baseline. These visualization comparisons demonstrate that our method effectively removes the false positives and matches the ground truth. To conclude, by using multispectral features within a two-stage deep learning framework, we achieve a 20% improvement in oil IOU performance. Finally, this is our reference. Thank you for listening.